Chapter 4, we're going to combine sections 8 and 9. Our objective is to learn to use the Pythagorean Theorem. Our essential question is, how do I use the distance formula and the Pythagorean Theorem and its converse to solve problems? Our vocabulary: Pythagorean Theorem, leg, and hypotenuse. We don't often take time to look at the history behind the mathematics. Here's a picture of Pythagoras. Pythagoras was born on the Aegean island of Samos, which is in the bottom right corner in the pink, and Samos is off of Turkey. He's best known for the Pythagorean theorem named after him, which relates to the side lengths of a right triangle. I'm going to give you a visual proof of the Pythagorean theorem. We also don't often look at proofs. All of the theorems in math came from somewhere, and they have a reason behind it, and they have to have a proof behind it to show that it truly works. So let's take a look at this proof.
You don't need numbers or fancy equations to prove the Pythagorean theorem. All you need is a piece of paper. There's a ton of ways to prove it, and people are inventing new ones all the time, but I'm going to show you my favorite, except instead of looking at diagrams, we're going to fold it. First, you need a square, which you can probably obtain from a rectangle if you ask nicely. Step 1, fold your square in half one way, then the other way, then across the diagonal. No need to make these creases sharp. We're just taking advantage of the symmetries of the square for the next step, but be precise. Step 2, make a crease along this triangle parallel to the side of the triangle that has the edges of the paper. You can make it anywhere you want. This is where you're choosing how long and pointy or short and fat your right triangle is going to be, because this is a general proof. Now when you unwrap it, you'll have a square centered in your square. Extend those creases and make them sharp, and now we've got 4 lines all the same distance from the edges, which will allow us to make a bunch of right triangles that are all exactly the same. Step 3, fold from this point to this one, basically taking a diagonal of this rectangle. Now we've got our first right triangle, which has the same shape and area as this one. Let's call the sides little leg, big leg, and hypotenuse. Rotate 90 degrees and fold back another triangle, which of course is just like the first. Repeat on the following 2 sides. The original paper, minus those 4 triangles, gives us a lovely square. How much paper is this? Well, the length of a side is the hypotenuse of one of these triangles, so the area is the hypotenuse squared. Step 4, unfold, and this time let's choose a different 4 triangles to fold back. Rip along one little leg and fold back these 2 triangles. Then you can fold back another 2 over here. The area of the unfolded paper minus 4 triangles must be the same, no matter which 4 triangles you remove. So let's see what we've got. We can divide this into 2 squares. This one has sides the length of the little leg of the triangle, and this one has sides as long as the big leg. So the area of both together is little leg squared plus big leg squared, which has to be equal to this area, which is hypotenuse squared. If you called the sides of your triangle something more abstract, like a, b, and c, you'd of course have a squared plus b squared equals c squared. So quick review. Step 0, acquire a paper square. Okay, step 1, fold it in half 3 times. Step 2, fold parallel to the edges anywhere you choose and extend the crease. Step 3, fold back 4 right triangles around the square and admire the area hypotenuse squared that is left over. Step 4, unfold and rip along a short side to fold back another 4 right triangles and admire the area one leg squared plus the other leg squared that is left. And that's all there is to it. Of course, mathematicians are rebels and never believe anything anyone tells them unless they can prove it for themselves. So be sure to not believe me when I tell you things like, this is a square. Think of a few ways you could convince yourself that no matter what the triangles on the outside look like, this will always be a square and not some sort of rhombus or parallelogram or dolphin or something. Or, maybe it is a dolphin, in which case you should define what a dolphin is and then show that this fits that definition. Also, these edges look like they line up together. Do they always do that? Is it exact? You don't need...
So let's keep going. After that proof, we see that the Pythagorean theorem comes down to a squared plus b squared equals c squared. Now you don't have to understand all of the concepts behind that, and I know it went very quickly, but it gives you an idea of where it comes from and that it's not just something that's made up. So this works every time we have a right triangle. This only works for right triangles. We always have 2 legs and a hypotenuse. The hypotenuse is easy to identify because it's the longest side, and it's the side that's across from the 90-degree angle. The legs would be the 2 sides that surround the 90-degree angle. So let's apply the Pythagorean theorem. What is the diagonal length of the projector screen? And in case you didn't know, most screens and most TVs are measured at a diagonal. So we have a right triangle because the corners of the rectangle are a right angle. So we can use the Pythagorean theorem to find that long side, which is the hypotenuse. So we would take 7 squared plus 3 squared equals c squared. We do some simplifying, get 49 plus 9 equals c squared. We end up with 58 equals c squared. Luckily, we just learned about square roots. So if we want to get down to just the length of c, we take the square root of both sides, and c equals the square root of 58, which is approximately 7.615. So that would be the value of the diagonal in feet. Let's try it again. Pythagorean theorem. Now we have two new sides, 12 squared plus 8 squared. 144 plus 64 equals c squared. 208 equals c squared. This final step is the new one for us. Take a square root of both sides. Square root of 208 equals c, which is approximately 14.42. So our length is about 14.4 feet in diagonal. Helpful hint, when using the Pythagorean theorem to find length, use only the principal square root. Remember, the principal square root would be the positive square root. We can also solve for something other than the hypotenuse. In this case, we're missing side b. So use the Pythagorean theorem and substitute what you do know. Obviously, if we're missing b, one of the sides we do know is a, and one of the sides is c. Again, the longest side is the hypotenuse, the one across from the right angle, and that would be 25, which is c. So that must mean a is side length 7. So 7 squared plus b squared equals 25 squared. Here's where our algebra comes in handy. We simplify both sides, so 49 plus b squared equals 625. Subtract 49 to get b squared by itself, and we have b squared equals 576. That is not the length of b though. We need to take the square root of both sides to get b equals 24. So just to show where that came from the square root of 576. Let's tell whether the given side lengths form a right triangle. If they truly form a right triangle, then the two smaller sides squared and added together will equal the longest side squared. So plug it into the Pythagorean theorem. 9 squared plus 12 squared needs to equal 15 squared. 81 plus 144 needs to equal 225. 81 plus 144 is 225, therefore they are equal, which means that it truly does form a right triangle. Let's try it again with 8, 10, and 13. We always know the longest side is c, so we'll take 8 squared plus 10 squared equals 13 squared. And I haven't mentioned this yet, but it doesn't truly matter which one is a and which one's b. Usually we just go in order, a being the smallest, b being the second largest, and c is always the largest. But a and b can be flipped around because we're just adding them together. So we get 64 plus 100 equals 169. Those two results are not the same, so those three sides would not form a right triangle. So the last thing we need to look at is the distance formula. The distance between 2 points, x1, y1, and x2, y2, on the coordinate plane is given by this formula. D equals the square root of x2 minus x1 squared plus y2 minus y1 squared. It just means we're subtracting the x's, subtracting the y's, squaring each of those numbers and adding them together, and then finding the square root. A lot of steps, but all it is substitution. So we want to find the distance between the points to the nearest tenth. So we have j and we have k. So let's look at where those points are located. So j is at the point -4, 0. K is at the point 0, -3. The reason we can't do the distance like we did previously is because these are not in a straight line from each other, they're at a diagonal. So essentially what we're doing is we're using Pythagorean theorem to figure out this, and that's where the distance formula came from. So keep those 2 points in mind. You might even want to write them down. And we're going to use the distance formula right here. So here's what this looks like. So let me rewrite the 2 points. We had j, negative 4, 0, and we had k, 0, negative 3. So where do these come from? This would be x1, this would be x2. So following the formula, we take 0 for x2 minus negative 4. This would be y1, this would be y2. So following the formula, we take negative 3 minus 0. Substituting in. If it helps to label your points, I find that's easiest, and then follow the formula. So now we follow order of operations, 0 minus negative 4. We get positive 4 squared. Negative 3 minus 0 is negative 3 squared. Take them to their powers, so we get 16 plus 9 gives us 25, and the square root of 25 is 5. Distance between j and k is 5 units. Let's check out L and M. So let's change those ordered pairs. So we have L, which is going to be at 4, 0. Label x1, y1. And then we have M, which would be at 5, negative 3. So again, we have x1, y1, or x2, y2. Substitute them in. So it turns into 5 minus 4 and negative 3 minus 0. After subtraction, we have 1 squared plus negative 3 squared. After exponents, we have 1 plus 9, which is 10. Square root of 10 is approximately 3.16, but it asks us to round to the nearest tenth, so our distance would be about 3.2 units between L and M. That's it. Make sure you filled out your notes. If you have questions, put those on the left-hand side. Otherwise, come up with good quiz questions to have there. Review your notes and complete the summary before class.